Hello, I'm Anton Amirov, work at Microsoft Search Assistant and Intelligence Group. And this work is done in collaboration with Chris Quirk, from the same group, and Jennifer Neville from Microsoft Research. I will start by describing the practical problem that we are trying to solve and the motivation for developing our techniques. In Microsoft, the data of each organizational customer of our cloud service is represented as a graph. It is promising to use this graph data to improve relevance in different scenarios, such as recommendations we make to our users. However, our goal is to build the representations of the nodes in a way that they can be used by the downstream models. So we want to isolate the downstream models from traversing the graph, especially if the models are working in the real time. And the requirements we have for those representations is that should be consistent across the graph, so that we want to be able to build the downstream model on some of the graph, on one graph or the set of the graphs, and for that model to be able to perform on the other graphs that it has not seen during the training. And another requirement that we have, so we want the representations to be task independent, so that we can downstream models can be trained and independently evolve, so that the representations we create act as a features, as a stable features. Okay. So to address the problem, we suggest two closely related approaches based on using random projections of different powers of the graph transition matrix. Random projections, which are essentially propagating random vectors through the graph, is a well-known technique used to create transductive embeddings for large graph, as it is computationally efficient and scalable. And our approaches demonstrate that random projections can also be used in a generalizable way. The intuition behind our methods is based on the hypothesis that dot products between rows of different powers of the transition matrix can be used as a set of features that contain about enough information about the node neighborhood to be useful in a variety of tasks. These features have another interpretation through the random walk probability, which make them invariant over graph isomorphism. And also it can be shown that they're generalizable for some, at least for some tasks. However, computing the exact powers of the transition matrix for large graphs can be computationally expensive beyond very low levels, since the transition matrix, powers of transition matrix quickly becomes dense. Fortunately, the random projections provide a way to approximate the features that we want directly without having to associate the powers of the transition matrix, as we have detailed in the paper. And another attractive, well-known property of random projections is the efficiency, both in terms of computational complexity and scalability. Random projections computation can be seen as a message passing operation with the sum aggregation, and that can be easily mapped to a MapReduce architecture. Direct application of these approximation techniques leads to our first approach that we call RP.product, where we do message passing of Gaussian random vectors up to some power, and compute dot products of the same row in projection of different powers of the transition matrix for the single node, and for the pair of nodes, we computed between the corresponding rows. And yeah, so for the pair of nodes, it also makes sense to use not just the pairwise features, but also the single node features for both nodes of the pair. But can we use the random projections directly as an input to the downstream model? And generally, it's not a good idea to use them in the general model architecture, as it will require a lot of instantiations of the random projections to make the model learn the generalizable features of the random projections rather than to try to overfit to the artifacts of the particular instantiations it was trained on. And as a solution, we want to add the knowledge that we know, the facts that we know about the random projections into the architecture of the model. And these facts are, one is that each index in a set of random projections is independently sampled. And so it should be independently processed. And also the order of the dimensions is not important, so that we should be using the set function to aggregate the embeddings, aggregate the processed random projections. So this, so this leads to this architecture. RP-CondNet, when we use one-dimensional convolutional network to project each dimension in a set of random projection vectors into processed vector, and then pull those before passing to a downstream task. And here the input projections, they are fixed for all the tasks, but the parameters of the convolutional network, they are specific to the downstream task. So the kind of significant difference between the two approaches is that RP.product, it actually creates the features for the downstream task. And here the features are the random projections itself. And what we are doing, we are prescribing the layer of the downstream model that should be consuming the random projections. But the parameters of this layer, they are trained together with the downstream task. Well, for evaluation, we need a data set that contains graphs drawn from the same distribution. And the Yelp open data set that contains businesses, users, and reviews, provides meets this criteria, provides a natural way to do this, since the data is segmented into metropolitan areas. So these are disjoint graphs that we can use for evaluation. And in another data set we looked is the Amazon product categories, where in this case we have artificially created the settings by splitting the data set into two halves and removing the edges between the test and train splits. Well, we compared our approaches with the set of isomorphic graph features that contain degree, page rank, EGANet, number of EGANet ages, and so on. And the GNN embedding created by the GNN that is trained for the link prediction task, and that is using these isomorphic features. As you can see on the Yelp data set, our approaches, they outperform these two, and the convolutional network is significantly outperforming the RP.product. However, the RP.product ensembled with the isomorphic features, it performs the best among all the things that we have tried. On the Amazon category predictor, prediction, we see kind of similar picture, but ensembling does not provide the boost here, so it's not shown. And gains from RP.product are less noticeable compared to the link prediction. Well, and in addition to node classification, we have evaluated the pairwise prediction task. And this pairwise prediction task, which we artificially constructed here, is we are trying to predict if two products belong to the same category, but we don't actually provide this category during the training. So it's just a binary classification. And yeah, so here we see that our approaches, they perform better than the link GNN or this isomorphic features. However, then another approach that we described in the paper, that if we use a node to vec embeddings, but both input and output vectors of the embedding, and they compute the cross dot product between all the vectors in the pair, that creates 10 features, then it actually creates a pretty strong contender in this case. Right, so, well, in conclusion, the suggestion techniques, they appear to offer competitive performance, at least on the tasks that we have evaluated. And these representations are relatively inexpensive to compute, especially compared to node to vec. And these computations can be easily scaled out. Yeah, like our approaches can be extended to weighted, directed, and heterogeneous graphs. For heterogeneous graphs, that, well, we can use the different transition metrics that belongs to different edge types. And yeah, thank you. And well, I hope that our work can maybe prompt some research in this direction, in the finding the embeddings that can be generalizable between the similar graphs. Thank you.
Yeah, okay. So sorry, my question is really about the distributed computation. So there's kind of this adjacency matrix to a certain power multiplied by some projection matrix. And I think the way that you talked about computing these things is that you can do it in a distributed way using MapReduce. So I'm kind of curious, like if you encounter, I've tried similar techniques on graphs, versions of the adjacency matrix, where the adjacency matrix can be like hundreds of millions or even billions of nodes. And even these distributed algorithms are pretty unscalable for matrix multiplication. So I'm curious if you encountered any problems in scaling this up, or if you had to make certain approximations or constraints to your graph size to make this work.
Thank you for the question. So here we are not instantiating the powers of the transition matrix. So what we do, since essentially we are producing the product of the random projection by the power of the transition matrix, and that can be achieved by the essentially by this multiplication. So this effectively, it is a message passing through the graph. So it does not have like real actual matrix multiplication. So yeah, this is all the well-known works that are faster P and rand and E that deal with the random projections. They are dealing in the case of large graphs, and rand and E, I think, very large graphs. And yeah, so that is not really kind of new property of the random projection. So that, but yeah, that's what we utilized. Yeah.